Good morning. First, I'd like to thank the organizers to this great meeting. I'm going to be talking about training viscoelastic materials. Basically, the question that I'd like to ask is how can you teach very simple elastic systems, complex elastic responses, and I'd like to also discuss, what are the important considerations of how training can affect the system, especially when you kind of push to do more and more difficult tasks. And just to give you a sense of what types of behaviors we'd like to
I don't think your mic is on.
Yeah, we cannot hear at the back.
Okay, so just to give you a sense of the type of behaviors I'd like to control, so I've written down a few examples. We'd like to control bulk material properties such as moduli, Poisson, so on and so forth. I'd like to be able to get spatially varying responses, such as this example here with the video that's not working. Basically, this is an example where I pinch one side and I get a response on the other side. This is inspired by allosteric proteins, but really want to get the broad types of responses. I would like these mechanical systems to do computations, various nonlinear behaviors, rate dependent dynamics, and so forth. The systems I'm going to be focusing on are disordered solids. So why disordered solids? So first of all, disordered solids are very common. You have glasses, crumpled cheese, polymers, Gaussian materials, and so forth. They occur broad set of length scales. They have a lot of interesting properties. There's first of all really a lot of degrees of freedom. They're free, they're kind of free. You don't have to build them. They're just there in the material. These systems often have a rough energy landscape, and this is kind of just an illustration. It's obviously a high-dimensional system, and the systems can have an enormous number of energy minima. And these systems are also often out of equilibrium. Their relaxation times are so large that they kind of get stuck. And lastly, these systems are often very frustrated. And I think an important question is, how does the physics of these sort of systems affect what the system can do? And I think it's somewhat of an open question, though. I think the expectation is that the more complex the system, maybe the more expressive it is. One kind of important aspect of these solids is that they're very malleable. What do I mean by that? Well, the systems don't quite, in some sense, these systems don't really have an intrinsic state. Their state really depends on how you prepare the system, how you drive the system, how you deform a system. So when you deform a system or you or kind of perturb the system kind of goes into different states. And there's been kind of a lot of studies on this. So people have shown that you can actually encode memories of a sequence of deformations and then read them out. If you just take many plastics and just put stress on them, they creep over time. They can change their shape. And even driving at a finite frequency causes them causes the eigenmodes to adapt in a very specific way that's related to the driving. What we want to do is exploit this kind of very strong dependence and history of perturbation to create non-trivial responses. So this is work that started with Nidhi Pashin, Andrea Liu, and Sid Nagel. So what I plan on telling you is, first of all, I would like to kind of present 3 algorithms to train different responses. And I would like to discuss a bit important considerations. How does the system converge? What's the convergence times? The capacity, robustness. And basically, one of the main messages that I hope to convey is that training causes the system to degrade. And I think it's a really important aspect that really affects the robustness, the capacity, and convergence time. And I think it's also a very robust feature in a broad set of systems. I'm going to start by giving a few examples of training algorithms. I don't have time to discuss all of these in detail. So the first thing I'll talk about is the model. The model is really the simplest model you can think about. It's a bonded network, just it's randomly generated. The details are it's not really important. And each bond is basically Maxwell viscoelastic material. Each bond, so it's a spring and a dash but in series. The tension of the spring is just depends on deviation from the rest length, and this kind of dash plot is responsible for allows the system to change to creep, to change its geometry, and everything I'm going to tell you about is in the quasi-static regime. So just to show you, this is not complete a toy model. Just to illustrate, I brought an example. This is silly putty. I'm sure you're all familiar with it. If you drop it, it bounces like an elastic solid. If I leave it, it will just turn into like a puddle. That's like a good illustration of this model. Okay, sorry. So this is the first example. So here, what I want to train is kind of this allosteric response. So just so basically, I have a source site where I squeeze, and I want to get some kind of a strain response on a faraway target site to basically transmit a signal. So the way I can teach a system is very simply, I grab the source and target and periodically squeeze the system over and over. I'm basically just showing a system what's the desired response. And as I'm doing that, I'm creating stresses in the system, which causes the structure to remodel. And then if you want to kind of check how the system is doing, assess the system, all I need to do is go squeeze this source and measure what happens in the target. I would like to show you a video, I hope it works, of how the system doesn't work, how the system evolves. Oh, now it's working. So basically, I'm only showing you these kind of readout cycles because the training takes a long time. The top, the green here is the strain on the source. This is the strain I apply. And the red is the strain on the target. And so basically what you see is that as I'm training for longer and longer periods, the amplitude is growing. It's basically converging to the desired response. And if you wait a long time, the system eventually gets there. So I'd like to explain a little bit what's the kind of motivation for this, how to think about it. So how do you think of, I would like to think of responses. So imagine grabbing a source and target and squeezing them independently. When you do this, you can measure elastic energy. This is like the elastic energy as a function of the source and target. And this is the unstrained state in the center where the energy is minimal. And if you deform a system in these different directions, energy can grow. Here, the stiffness is larger. Here, it's softer. And now imagine I start from the undeformed state, apply a deformation, and then let the system relax. So the system relaxes to force balance. Force balance is state with minimal energy under the applied strain. So basically, the system is going to flow in this state down here. And basically, what I'm trying to convince you is the response is more or less follows the soft direction, and you can do this more precisely within linear response. And the error deformation, if this is the desired response along this direction, the error scales the ratio of these the longitudinal to the transverse stiffness. So what happens in training? With training, plasticity kind of changes the structure. What does a dashpad do? Dashpad basically relaxes elastic energy. So if, for example, you pull one of these bonds, its stress lengths will kind of grow to reduce elastic energy. So when I'm training, basically, so if I kind of deform a system and set at a given state, a given strain, it's going to reduce the energy at that state. And if I drive it periodically, basically it just creates kind of an energy valley. It carves out the energy valley. Another example of a training algorithm. I have a different goal. I want to be a bit artistic. I want to paint pictures, but they're not just regular pictures. They're pictures that are force balance. So this is an example. You have 3 kinds of bonds. Blue bonds have 1 unit of tension. Red have a negative unit of tension, and then you have gray bonds, which are kind of difficult to see, and those are kind of these learning degrees of freedom. And the training algorithm is very simple. alternate between two states, between a free state and a clamped state. The free state is frozen. I assume it doesn't evolve. You can relax this assumption, but I won't really discuss this. And during the clamped state, I basically apply a tension or a force to these target bonds which I'm trying to control. And basically, the training rule says that the tension that I apply during the clamped state evolves in proportion to the tension of the desired and minus the free state. This is not equilibrium propagation. It look at the first glance, it might look like that. It's actually, I think the best analogy is just a PID, or it kind of integrates over the air. The last example I want to give is how you can create rate-dependent responses. So again, this is all the same system of springs and dashpots. And here my goal is to control the response. The response is a function, create rate-dependent responses that the response depends on the rate at which I actuate it. And basically, I use the fact that at fast time scales, system behaves elastically. So basically, behavior is really dominated by the springs. The slow response, however, depends on the dashpots and kind of the relaxation rates of the dashpot. So how high is the relaxation rate of the dashpot? And basically, the training rule says I'm going to change the relaxation rates of dashpots, and I'm going to assume that the dashpots degrade. So if I take a dashpot and if it undergoes some kind of plastic deformation, I assume these dashpots degrade at a rate that depends on the rate of plastic flow. Basically, all I do, I use these with this assumption, I just actuate along the desired response, and basically I can get responses that behave very differently at fast deformation rates and at slow deformation rates. So this is like the ratio of the response to the applied strain, and for fast actuations it's positive, and for negative deformation it's negative. So the system behaves completely opposite at fast and slow formations. So now for the remaining my talk, I want to kind of focus on this first system. What I want to do is kind of see what happens when I kind of push the system and try to give it a more and more difficult function. And the way I'm going to do it, it's obviously not the only way. What I'm going to do is I'm going to try to control not just a single target site. I'm going to control multiple target sites. So I have a single source site. I want to control the strain on multiple target sites and see what happens when I vary the number of target sites. I want to see what's the capacity of the system and how the system fails when I try to control too many sites. This is work by Himangsu Baumik. And the first thing we looked at is the error. How does the system converge? And so you see the error is a function of number of training cycles for different number of targets. The first thing you kind of see is that as you train responses with more and more targets, convergence becomes slower and slower until eventually the system doesn't look like it's converging at all. If you kind of fit the error function time at long time scales, it's approximately a power law. And so you can kind of measure this exponent alpha. And if you plot the exponent as a function of number of targets per node, what you find is that this kind of exponent decreases until it appears to vanish what appears to be it looks like a critical point. This defines like a threshold between responses that converge and don't converge. And if you look at different system sizes, it appears that the number of sites you can control is extensive. And I just like to emphasize that this convergence is kind of very, very slow. So if you ask yourself, how many cycles do I need to train to get a certain desired error? I train until this error, and I assume this exponent varies linearly. So if you kind of use these assumptions, you find that the relaxation time has this kind of Vogel-Fulcher-Taman law, which is very common form in the glass community. Basically, it's an exponential of something that diverges. Basically, the main point here is that you have a kind of non-trivial critical point that appears to control how fast this converges. And what we were trying to really figure out is where these very slow relaxation times coming from. So we started looking at the energy landscape. So basically, we're creating an energy valley, and the energy, there's two ways where the energy valley, or there's a number of ways the energy valley can change. You can look at the longitudinal direction, and you can also look at the transverse direction. But first, we look at the longitudinal direction, and if you look at how the energy along this training path decreases, we don't really see a signature of these very slow time scales. And then we wanted to look at the transverse directions. So how do you look at the transverse directions? Do you look at the Hessian? So it's a matrix of second derivatives of the energy. And if you diagonalize it, you can find kind of eigenfrequencies or stiffness in different directions. And then if you can go on and plot the density of states, it's just a histogram, and so you can get the distribution of these eigenfrequencies, and this is how typically it looks before training. It's roughly constant, and then it falls quite suddenly at a characteristic frequency, which really depends on the coordination number. So this is how the density of states looks as I train the system, and black curve is before training. Basically, what you see is as you have more and more targets, the density of states shifts to lower and lower frequencies. So this, I think, at least for us, was quite surprising, because disordered elastic networks they usually have a certain typical frequency, which is this omega star, and you have to kind of work hard to get something which is different. And here you see really that the frequency seems to be that you're getting lower, not only you're getting lower frequencies, it seems that even that maybe the density of states is diverging. And you can also look how the density of states changes over time at the critical point. And if you collapse the curves, it seems that this kind of gap frequency decreases as a power law, tau to minus 0.25 or something of that order. Really, I guess the main point here is that as you're training a system, you're not just getting certain desired responses. There's an unintended consequence that the system is degrading, and this affects the rigidity. And when you train for the maximal capacity, the critical point, the system looks like it's actually losing its rigidity completely. So why does this mean? So how does this explain these very slow convergence? So you can think of the response in terms of, you can think of the response in linear response. The strain is proportional to the inverse Hessian, and you can do this expansion in terms of eigenmodes. So these are the two lowest eigenmodes. So the first term would argue is the trained response. So we're trying to create a very low energy. This is the kind of this low energy value we're trying to create. And omega 1 is this transverse modes. So basically, this term is kind of a competing direction. And if you would like to estimate the error, it's just the ratio of these two frequencies. So basically, the system fails because you have these competing spurious modes. The system doesn't just go along the desired path. It goes along these transverse directions, which have this low frequency. This also causes very slow convergence because you're trying to create this low energy valley. Then when you're doing this, you're also lowering the stiffness in the transverse directions. Then you need to train even more to even make this energy valley deeper and deeper. And I think, I'd like to first of all try to convince you this phenomenon is quite general. So first of all, there's kind of a recent preprint by that also saw this effect in other systems such as resistor networks. But I think ultimately, I think this even happens in systems like the Hopfield model. So the model, you try to encode memories in the minima. And as you kind of try to encode more and more memories, you're increasing the difficulty. These kind of minima becomes shallower and shallower, and at the maximal capacity, these minima are no longer minima. And basically, those points are essentially flat, and that's what would argue is just the same or very similar vanishing frequency. And I think this has a very important consequence. You could imagine, let's say you want to reuse your system. You want to train one task and then train another task. You want to change the function of your material. And as you change tasks, this kind of gradation doesn't go away. As you train the system more and more tasks, you have this continual drift of the density of states to lower and lower frequencies. This is for these elastic networks. You can also tried looking at resistor networks or change through equilibrium propagation. And again, you have this kind of memory of training. You have this degradation and memory of training. So these low frequency modes are very strange, are very not atypical of stored elastic mediums. So we're trying to understand where these failure modes come from, and if we can understand it, maybe we can try to reduce this degradation. And we can actually regularize these failure modes. So we started looking at these eigenmodes. And the first thing we looked at is a participation ratio. And the participation ratio kind of measures how local or how localized these eigenmodes are. But we see these eigenmodes are very, training causes these eigenmodes to be quite localized. So this means that it's a local effect. And we looked a lot at the eigenmodes, and the conclusion that we got is that what's happening is that bonds are aligning. The angle between bonds becomes very, very small. So if you think in terms of constraints, as Lisa discussed in detail, basically when bonds align, these two constraints become redundant. You get a state of self-stress, and you can get a low frequency mode. So in order to kind of prevent this, a natural thing to do is try to prevent bonds from getting small. So what we did is we added an angular potential. So basically, if the angle becomes too small, we add a kind of force that prevents this, and we wanted to see what happens. So we're trying to restrict the space of solutions. So this angular force, it mostly affects training. It turns out that after you train the system, it doesn't really do very much. It just acts as a constraint. So what we found is that adding this constraint really has a positive effect. So we find that really it can. So these are curves that show training without repulsion and training with repulsion, and we see this exponent alpha becomes larger. We're able to train more targets. We're able to train at larger amplitudes and so forth. And it's really had a lot of beneficial effects. It can accelerate convergence. Increase the capacity. You can even train responses that previously didn't converge. And the last thing, which I'd like to mention, also increased robustness. So I think to some degree this is somewhat surprising, because usually if you restrict the space of solutions, you're kind of preventing a system exploring, the full possible states. And here, in some cases, it can be. In many cases, it has a very positive effect, and even converges faster, which I think for us was a surprise. So how do we think of robustness? So what do I mean by robustness? Robustness means that after I train, for example, let's imagine I add some random perturbation. I change the rest length by some random factor, it's an amplitude delta. And you can kind of work out in linear theory what you expect the robustness to be. And basically the expectation is that the error changes by an amount that's kind of inversely proportional to this transverse frequency, this kind of gap frequency. So basically, you want your energy value to be deep. If it's very shallow, the system is not going to be robust at all. And so here you can kind of really compare training without repulsion and with angular repulsion. Here, for the angular repulsion, without adding these perturbations, the system converges much more slowly. So these full curves are training without repulsion. These dashed curves are training with repulsion, and you can see that once you add this perturbation, the system becomes much less robust, and even the error can actually increase. So even so, the system that convert the systems that this angular repulsion in this case didn't converge as much as the case with no repulsion, even though the error kind of is larger. When you add this perturbation, they're actually more successful. Okay, so this is kind of a picture that we have in mind. What happens when you change the difficulty or complexity? So, increasing the difficulty first of all increases the convergence times. It kind of increases this effective material degradation, and it also reduces robustness. Really, what controls a lot of this behavior, at least in our view, is that gradation is what reduces robustness, and degradation is also responsible for these long convergence times. So I'll just mention a summary. So basically, the main message, we're able to train with various algorithms, different behaviors. The advantage of training versus design and fabrication is that you don't need to go in and manipulate by hand each degree of freedom. The system that solves the problem by itself. It's probably insensitive to a lot of the microscopic details. And I think to some degree, it's probably more useful for creating complicated responses than by design. A lot of the convergence is governed by unusual critical point, and failure seems to occur through the formation of a lot of spurious low-frequency modes. And lastly, constraining a space of solutions can have a really positive effect and even accelerate convergence, increase robustness, reduce degradation, and even increase capacity. Thank you for your attention.
The histogram of eigenfrequency, are you sure that it goes to 0 or below a certain value?
So which?
Binary hash frequency where below certain frequency there is no response, and above that there is.
I'm not quite sure what you mean. Maybe you could.
What I'm reading here is below certain frequency, the system does not respond.
I mean, the quasi-static response is it's really like vanishing frequency, and you do have, so responses at low frequency are dominated by the lowest frequencies. So you do get responses.
Thank you for the topic. I'm wondering about the extra regularization that you add. So
Yeah.
I'd like to know if first the intuition it should be that when you apply this extra regularization, you get a larger gap between the desired modes and the rest. And if so, you have an intuition why that happens for this regularization.
You're asking why does this regularization prevent these low frequency modes from forming?
Yeah.
Well, I mean, it seems that the failure modes are, the reason you get these low frequency modes is because you have bonds at the line. Sorry, I'm going there, right? Sorry. So because the angles between bonds become very small, so we get these low frequency modes. I assume for a resistor network, just the resistance becomes very small, so if you prevent from bonds, I'm not sure it's the only failure mode. I'm not sure maybe you can have global you can have large scale modes that, but it seems to be the one of the dominant failure modes.
I have a very closely related follow-up question, which is, have you started to think about, like, sort of for general systems, like in this case, you sort of looked and saw that there was a localized mode and there was an intuitive thing to do to correct it, which you did, which is very cool. But sort of, is there a way to sort of systematically, like, look at the Hessian and decide, I want to correct for these? Or do you think it's going to be a case-by-case basis, like you said, for resistor networks or biological networks or whatever?
I mean, I wish I knew the answer. I mean, I guess the participation ratio, first of all, is kind of an indicator whether it's local effect or a global effect. And if it's a global effect, you can't change your local rule. Like if it's a global effect, probably can't affect your local rule to prevent it.
I couldn't help just keep thinking about the fact that your constitutive, model for each element is a Maxwell fluid, and they fluidize at low frequencies. I mean, like your silly putty, right?
Yeah.
Does that have anything to do with your degradation? If you would put the damper in parallel rather than series, would this change?
Well, if you put in parallel, then the system can't really change its structure. I mean, if I had to guess, I would imagine, driving systems, causes the system to explore various state space, and they think that the system tends to evolve towards. So this is, I don't have proof of this. So this is what I would imagine. The system evolves towards states with lower rigidity. So, imagine you take these systems and you turn on a thermal bath. Can let the system evolve. So system 1 to evolve to state with larger entropy. And states that have larger entropy probably have more softer directions. So that's how I would interpret it. But I think it's kind of an interesting question. Why do systems tend to evolve towards to be softer? And I don't have a better answer, unfortunately.
Okay, let's call this because of
My question.